Hello, I am Soledad Pech and I'm going to present you my project called Rheological Characterization of Ramon Starch, Brosimum alicastrum suspension with potential use for food packaging film. I will now give you a brief introduction. One of the most effective strategies to reduce the problem of plastic pollution is to develop biodegradable materials that can replace it. Currently, research on biodegradable materials mainly focuses on synthetic and natural polymers. Several natural polymers are being used as raw material for constructing biodegradable materials, such as proteins, polysaccharides, and lipids. Among the natural biodegradable materials, starch-based biodegradable materials are widely studied and applied. The above is because starch is a renewable, natural material, low-cost, non-toxic, biocompatibility, abundant, and conform films. Besides, starch can be obtained from different sources that do not participate with human feeding and can be used as raw materials for materials obtention, such as Ramon seeds, Brosimum alicastrum, a tree found in southeastern Mexico. Its average production of seeds is 95.5 kg per year, and each seed possesses 92.57% of starch with an amylose content of 25.36%. Natural starch generally exists in the form of granules, which are spherical, oval, or irregular in shape, with diameters ranging from about 0.1 to 200 micrometers depending on the source and maturation stage. Starch granules are insoluble in cold water, but if they are heated above a specific temperature over water, they absorb water and expand. Moreover, the high temperature and excess water condition of starch gelatinization do not become relevant to all food uses of starch. At relatively low temperatures, the crystalline region of the starch granules maintains its integrity. However, suppose the starch suspension continues to be heated. In that case, the granules will continue to absorb water and the crystalline regions will swell, eventually disrupting the starch granules and forming a hydrophilic colloidal solution. This process is known as the gelatinization of starch. After gelatinization, when a starch solution is cooled to a sufficiently low temperature, starch molecules reorganize, hydrogen bonds reform, and other structures are re-established. At the same time, the viscosity of starch suspension increases and gel forms. The structure and properties of starch are closely related to the formation and properties of starch-based biodegradable materials. This work focuses on evaluating the obtaining of starch from Brosimum alicastrum using two extraction methods and how it affects its rheologic and physicochemical properties. The next section is material and methods. The next section is material and methods. The starches were extracted according to the methodology reported by Pechko et al. And were named RS1 for the one obtained with distilled water and RS2 with the sodium hydroxide solution. The first is isolation using distilled water. Ramon flour was soaked in distilled water for 24 hours and the moist Ramon flour was then blended at high speed for 2 minutes. The slaughter was washed through a use number 100 and 200 sieve. The filtered product was centrifuged at 2500 rpm for 20 minutes, and the resulting supernatant was decanted. The starch granules were washed 3 times with distilled water and then dried in a convection oven at 60 degrees Celsius for 24 hours. Finally, the starch was stored in hermetically sealed glass containers until subsequent analysis. The next method is alkaline steeping. Ramon flour was soaked in 500 milliliters of 1 grain for 1 kilogram sodium hydroxide for 18 hours. Then the moist flour was blended with a blender at a high speed for 2 minutes, filtered through screens accordingly, and centrifuged at 2500 rpm for 15 minutes. The bottom starch layer was reslurred and washed with 1 grain for 1 kilogram sodium hydroxide and water, then neutralized with 1 mole per liter of hydrochloric acid, 2 pH, 6.5, and centrifuge. The starch was then washed with distilled water 3 times and then dried according to the above procedure. Raman spectra of starch sample were obtained on a Rheological in via Raman spectrometer equipped with a near-infrared ND-JAG laser operated at 1064 nanometers and a liquid nitrogen colored germanium detector. The starch sample, 4 milligrams, was placed into a small aluminum sample cup. A 100 milliwatts laser power was used for sample excitation, and the scattered radiation was collected at 180 degrees for each spectrum, an average of 1024 scans were performed at a resolution of 4 cm over the 3500 to 0 cm range. The percentage of amylose and amylopectin in each sample was obtained with this determination. Solubility pattern and swelling power of the starches were determined using an aqueous suspension on 1% RS1 and RS2 weight for volume, were heated in a water bath at constant temperature 60, 70, 80, and 90 degrees Celsius and shaking for 30 minutes. Each suspension was cooled and centrifuged at 3000 Gs for 15 minutes. The decanter was reheated and the soprano was placed in a vacuum stove at 120 degrees Celsius for 4 hours. Solubility and swelling power were calculated by means of equations 1 and 2, respectively. The morphology of starches were examined by scanning electron microscopy, SEM. Starch samples were mounted on a metallic slide and the examination was performed with a scanning electron microscopy JSM 6360 LB electron probe microanalyzer and 15 kilovolts in low vacuum. The particle size distribution and Sauder mean diameter D32 of the samples were determined in a particle size analyzer called LS100. 15 milligrams of powder dispersed in water and continuously stirred was fed to the analyzer. The Polydispersity index, span, and D32 values were calculated using equation 3 and 4, where Di is the main diameter of the starch granules, Ni is the number of starch granules, and D10, D50, and D90 are the diameters at 10, 50, and 90% of cumulative volume, respectively. RS1 and RS2 dispersion, 5% weight for weight, were heated at 90 degrees Celsius with magnetic stirring for 20 minutes and left cooled down to 25 degrees Celsius for 15 minutes for obtaining gelatinized RS1 and RS2 dispersion. About 3.8 milliliters of samples gelatinized sample was loaded into the parallel plate geometry of a Discovery HR2 rheometer. A gap of 0.5 mm between plates was used as some RS1 and RS2 granules exhibit the size of about 130 micrometers and for allowing for granule swelling upon gelatinization. Samples were allowed to relax for 5 minutes after loading for a structure recovery. Fluff cures were determined by varying the shear rate from 0.01 to 1,000 seconds. The obtained data were described using the following power law model, equation number 5. The viscoelastic properties determined under oscillatory shear conditions. The strain sweeps were carried out in the range from 0.01 to 100% in the LPR range, 1 Hz. The storage G' and loss G" moduli. All the experiments were carried out at 25 degrees Celsius. All measurements were done by triplicate and data were presented as the means plus or minus standard deviation. Data were processed using one-way analysis of variance ANOVA and Tukey means comparison analysis with a significance level of p less than 0.05. Now I will tell you about the results. The percentage of amylose was 25% for RS1 and 27 for RS2. In addition, characteristic starch bands were found as presented in the table with their respective assignments. Concerning the solubility percentage, RS1 presented higher values from 2% to 40%, while RS2 presented from 2% to 29%. For swelling power, RS2 showed higher values from 3% to 18% and RS1 from 3% to 15%. This was done for 4 evaluation temperatures. Some micrograms show uniform granules of different size. The mean diameter D32 was similar for both cases and the polydispersity index. Apparent viscosity were for RS1 4.69 plus or minus 0.38 Pascal second and RS2 was 9.07 plus or minus 68 Pascal second. The flow behavior showed high correlation values R2 equal 0.99 with a power law model. A storage modulus was greater than loss modulus, indicating typical viscoelastic behavior, predominantly elastic. And finally, the conclusion. A starch was obtained from Ramon seeds, Brosimum, alicastrum through two methodologies with different extraction medium. The amylose content was obtained by Raman and was similar in both cases. However, the solubility percentage was higher for RS1, while the swelling power was higher for RS2. The average diameter of the starch granules and the polydispersity index were similar. As for the rheological properties, the apparent viscosity was higher for RS2. The flow behavior 50 with the power law model and a viscoelastic behavior was also observed. And I would like to thank postdoctoral program for indigenous Mexican women in science, technology, engineering, and mathematics of Mexican Council of Science and Technology Center for Research and Higher Studies in Social Anthropology and International Development Research Center, Canada. Thanks for your attention.